Hello, can you see my screen?
Yes, ma'am.
Okay. So, yesterday we discussed construction of confidence interval for single mean and single proportion. Today we will discuss construction of confidence interval for difference between two means and difference between two proportions. Okay. So, sometimes we are interested in finding differences. For example, uh, let us say we want to see if adults infection rate of adults is more than say children in case of COVID. Okay, so I'll have some infection rate in adults which I denote by P1, then I'll have some infection rate for children which I'll denote by P2. We will estimate from the data P1 hat and P2 hat. Okay, so what is of interest to us is P1 hat, sorry, is P1 greater than P2 or is P1 less than P2 or are they equal? So, we want to answer such type of questions. So, for these it we can compute confidence interval for the difference, and then what happens if suppose my 0 is somewhere here and if I construct confidence interval for this difference and if that interval is something like this, that would mean that P1 minus P2 is 95% likely to be on the right side of 0. Okay. So, in such a scenario we will conclude that P1 is larger than P2. Okay. On the other hand, if my 0 is here and if the interval for P1 minus P2 is here, then we would conclude that P1 is smaller than P2. And the third case is where 0 is included in the interval. So, if interval is like this, then we will conclude that P1 is equal to P2, that is the infection rate is same for adults as well as children. Okay. So, this is one example where we need confidence interval for difference between proportions. Okay. So, how do we compute confidence interval for difference between proportion? For single proportion, we saw that if P hat is my estimate, then P hat minus 1.96 under root P hat 1 minus P hat upon n to P hat plus 1.96 under root P hat 1 minus P hat by n. This becomes confidence interval for P, single proportion. Do you remember we discussing this in the last lecture? Hello? Hello?
Yes, ma'am.
Okay. So, now we have to do something similar for P hat P1 hat minus P2 hat. What we know is variance of P1 hat would be P1 hat into 1 minus P1 hat divided by N1. Okay. This will be my variance of P1 hat. Variance of P2 hat would be P2 hat 1 minus P2 hat divided by N2. Correct? Okay, so far I am just trying to generalize from here. Now, in addition to this, we will assume that the two populations, so the population in which we compute P1 hat and the population in which we compute P2 hat, these two populations are independent. That would be our assumption. Okay, these two populations are independent. As a result, what would happen? As a result, we would have variance of P1 hat minus P2 hat would be variance of P1 hat plus variance of P2 hat. Okay. We will not have covariance term because these two are independent. Do you know what is covariance? Do you know this term?
No, ma'am, we don't.
Okay, fine. So we'll study this later. As of now, you should remember that this formula, the formula that we wrote here, this works only when populations are independent. Okay, if the populations are dependent, then things are not that simple. Okay, we need some adjustment. Okay, we will see it later when we study regression. Okay, so this is fine. Now that tells me that variance of p1 hat minus p2 hat would be p1 hat 1 minus p1 hat upon n1 plus p2 hat 1 minus p2 hat upon n2, and once I have variance I will again use standard normal theory. Okay, so my confidence interval, if I want 95%, my 95% confidence interval for p1 minus p2 would be p1 hat minus p2 hat minus 1.96 times square root of p1 hat 1 minus p1 hat upon n1 plus p2 hat 1 minus p2 hat upon n2, comma p1 hat minus p2 hat plus 1.96 times p1 hat 1 minus p1 hat upon n1 plus p2 hat 1 minus p2 hat upon n2. Okay, is it okay?
Yes, ma'am.
So let me take one example. So there were some scientists who were interested in examining whether smoking history has any relationship to the need of hormone replacement therapy. Okay, so there were two groups of women. One group of women was actually taking hormone replacement therapy, and there was other group of women who was not undergoing any hormone replacement therapy. And then they asked these people, did they used to smoke in the past? Okay, so in this group, in the HRT group, there were 220 women, out of which, from which 29.3% women said that they used to smoke regularly. Okay, at some point in their life they were regular smokers, and there were 106 women who were not undergoing any hormone replacement therapy, and out of them 17.3% women said that they used to smoke regularly. Okay, so now just looking at these values, it seems that yes, the proportion of smokers is high in the group which required hormone replacement therapy, whereas proportion of smokers is low in a group which did not require hormone replacement therapy. However, we don't know whether this difference is actually high enough to make such conclusions, whether this difference is statistically significant or is it occurring just by chance. Okay, difference could occur just by chance. So we need to construct confidence interval for this difference. Okay, so what I have, n1 is 220, n2 is 106, p1 is 0.293, 29.3%, and p2 is 0.173. So using these we need to construct this. So p1 minus p2 will be 0.12 minus 1.96, and then we have to compute this quantity. Okay, p1 into 1 minus p1. So can someone tell me these values? p1 hat into 1 minus p1 hat. Yes. Can someone compute p1 hat into 1 minus p1 hat? You are allowed to use calculator if that is what stopping you. Perhaps something like this. Am I right? Is anyone trying to compute?
Yes, ma'am. Point 2071 something.
Okay. And now the overall thing.
I don't have my scientific calculator. The square root would be difficult to do.
Okay. None of you have mobiles?
Ma'am, we are taking classes on a laptop, so it will take time to compute it
Sure.
on.
Okay, okay. Let me write. Okay, so this turns out to be 0.12 minus 1.96 into 0.05 roughly. Okay. So my 1.96 into 0.05 is 0.098. So I have 0.12 minus 0.098, which gives me 0.022 as the lower bound, and the upper bound will be just with the positive sign. So it is 0.12 plus 1.96 into 0.05, so that is 0.218. Okay, so the confidence interval is 0.022 to 0.218, and somewhere here we have 0. So we are marginally to the right of 0. So we can conclude that yes, the proportion of smokers in the first group is higher than the proportion of smokers in the second group. Is it okay? How you do these calculations? Can you solve such examples?
Yes, ma'am, we can.
Yeah. Now, so this is for difference between proportions. Similarly, now we have to compute for difference between means. Okay, because sometimes we may be interested in difference between means. For example, um, if I have say uh, one group of students, say group of students from school A, and I have their scores, and then I have group of students from school B and I have their scores, and I want to check whether say school A students tend to score higher, okay, or do CBSE students get more marks than say state board students, something like that. If I want to test, then I need difference between means. So the theory remains more or less the same. Okay, so we will again use the fact that variance of x bar is sigma square by n. So variance of x1 bar will be sigma 1 square by n1, variance of x2 bar will be sigma 2 square by n2, we will again assume that the two samples and the two populations from which the samples come, they are independent. So variance of x1 bar minus x2 bar will be variance of x1 bar plus variance of x2 bar. So this would be sigma 1 square by n1 plus sigma 2 square by n2. Okay, and hence the confidence interval would look like x1 bar minus x2 bar minus 1.96 times square root of sigma 1 square by n1 plus sigma 2 square by n2. Of course, sigma 1 sigma 2 would be unknown, so we estimate them using sample standard deviation, and upper bound would be x1 bar minus x2 bar plus 1.96 times square root of sigma 1 square by n1 plus sigma 2 hat square by n2. This is 95% CI for difference between the means. Okay, this is 95% CI for difference between the means. Okay, so let me take one example again. So this data is from 70 patients who had some ulcers in their legs. Okay, and two different treatments were tried. Okay, so one group of patients, so 35, the groups were equal sized. So first 35, randomly selected 35 people, they received treatment A. Okay, they received treatment A, and treatment effectiveness was measured in terms of reduction in leg volume as determined by water displacement. Okay, and for treatment A, the mean turned out to be 95 cc. Okay, mean reduction turned out to be 95 cc, and standard deviation of that was 25. For treatment B group, the mean reduction turned out to be 125 cc and standard deviation is 30. So if we just look at this data, it seems that in treatment B, mean reduction seems to be higher. So again we would like to check whether this is statistically significant, this difference is statistically significant, or is it just a coincidence. So what we do? So we again compute x1 bar minus x2 bar. So here x1 bar minus x2 bar will be 30. Okay, and sigma 1 square by n1 plus sigma 2 square by n2. Here n1 and n2 both are 35, so this becomes simply 25 square plus 30 square divided by 35. Okay, so 625 plus 900. 625 plus 900 would be how much? 1525 divided by 35, and we have to take square root of that. So that turns out to be roughly 6.6. So this is 6.6. So I'll have 30 minus 1.96 into 6.6 comma 30 plus 1.96 into 6.6 as the confidence interval. So that gives us the lower limit turns out to be 17.1, roughly 17.1, and the upper limit turns out to be 42.9. So this means that my confidence interval again is, oh, there is some problem. Can you see the problem? Can you see what went wrong? Hello? Hello? Can you see any problem here?
Is there one?
Sorry?
Is there a problem here?
Yes, there is. That's why I'm asking. There is. See, x1 bar minus x2 bar is 95 minus 125. So it should be minus 30, not plus 30. Correct? Because that changes my conclusion completely. If I change the sign, my conclusion would become opposite. So this is minus 30. So my interval actually becomes minus 42.9 to minus 17.1. Okay. So this interval is completely to the left side of 0. Okay, minus 17 will be somewhere here, minus 42 is somewhere here. So the interval is completely to the left of 0. So we would conclude that the first group has smaller mean than the second group. Mu1 is less than mu2. Okay. Is it okay?
Yes, ma'am, got it.
Yeah. So this is how we use confidence intervals for mean difference between means or difference between proportions. Yesterday we saw confidence interval for single mean and single proportion. Now in the next lecture we have to start what is known as testing of hypothesis. So here we are informally concluding these things on the basis of confidence interval, that if mu1 is less than mu2 or p1 is greater than p2, etc. But in the next lecture we will have more formal introduction to testing of hypothesis, and then we will also compare duality between confidence interval construction and the testing of hypothesis. So if there are no doubts, then let me stop here. Thank you.
Okay, thank you, ma'am.